In this video, I will present our work on contextual learning in few-shot object classification. Recall that the goal of few-shot learning is to train a model in such a way that it can learn new classes from a very small number of examples. However, most current methods tend to consider objects in isolation. As we can see on these images, these popular benchmarks generally have only one centered object. On the opposite, images in the real world can be more complex. They can contain many different objects. This scenario has been neglected so far in few-shot learning, and while it can be more relevant for real applications, complex scenes also open the possibility to supplement visual information with semantic relations. And those are important. It has been shown that it is generally easier for humans to learn a new concept when the learning process happens in context. For instance, suppose that I want to teach you that this object that you don't know yet is a corkscrew. To learn this new label, your brain will not only memorize the appearance of the object, but also encode the other objects that you already know in the scene, like the bottle of wine and other items related to food. Then, the next time that you see a similar object, maybe in a kitchen, the context will help you to recognize that this is a corkscrew, this object that you saw just once. This is known as contextual cueing and is very important for continual learning and incremental learning in humans. In our paper, we propose to include these ideas of contextual learning and contextual cueing in a few-shot setting. We represent the context elements by the base classes that appear on an image, and we encode them with their word embeddings. Then we develop two modules to leverage semantic relations between the novel class that must be learned and concepts that are already known on the image, the base classes. The first module is a class condition attention module that learns to weight the most important elements from the context while learning a novel class. The intuition is that all co-occurring objects are not equal. For instance, in my previous example, the bottle of wine might be more important to include in the semantic representation of a corkscrew than a wall or other objects that are irrelevant. CCAM will learn to give more importance to these objects and ignore out-of-context classes. Then the second module is a gating mechanism that learns to adaptively combine features extracted from the image with features extracted from the context. We experimented on visual genome and open images, which are large-scale datasets of thousands of complex scenes images with many objects on each image, and hundreds of classes. Since our model builds on prototypical networks and AM3, we compare our context-aware model with these baselines. We can see that considering the context significantly improves the accuracy, even in one shot, where there could be a risk of overfitting a particular context. Here, we visualize some of the weights that were given to co-occurring classes when our model needed to learn the classes shown at the bottom. We can see, for example, that the classes that are considered the most important while learning the concept of pa were cat or mat, while less relevant concepts such as bathroom or tiles are mostly ignored. Now, since we aim to study the contribution that context can have in a low data regime, we used an oracle to annotate the context elements. However, in real applications, we will need to employ an object detection model and classify the base classes in test images. The object detection model will make mistakes, so here we simulated the scenario by randomly switching round-trip annotations with a probability p-noise. We can see that our context-aware model still outperforms models that ignore the context, even if there are a lot of mistakes in the annotation of the context. So this suggests that our approach could be worth investigating in combination with recent few-shot object detection models as future work. Finally, we observe that CCAM implicitly learns and enriches semantic word embeddings. In this table, we show a few examples of classes and the 10 words that are considered the most relevant from the whole set of base classes, and not from a particular scene as we have shown previously. We can see that the contextual words are very reasonable, even if CCAM is only implicitly trained to learn these semantic relations. For more details and results, please see the paper and feel free to send us your question. Thank you.